Hello, another past paper question, this time on empirical formula and polymers. So related topics to the empirical formulae and addition polymers contained in this question are moles calculations, monomers, repeat units, skeletal formula and hydrolysis. Obviously links to polymers in year 2, which would be condensation polymers. Same format as always, there it is. I will cut to the chase, but you know what to do. So here's the question, have a look at it, pause it, press play when you're ready. So with these type of questions, I like to use a table. I think it's really clear to show you working out. We've got the atoms, we've got the percentages, the relative atomic masses. We can work out the amount of substance and the relative amounts of those two different atoms. If we had 100 grams, there would be 88.2 grams of carbon and 11.8 grams of hydrogen. We can get the relative atomic masses from the periodic table. Mass over molar mass gives us those amounts of substances, and we get the ratio by dividing through by the lowest whole number. The lowest whole number ratio is not 1.00 to 1.61, so we have to kind of multiply through by a common factor to find that. A tricky ratio, I think you'll agree. But if we try to get it to a lowest whole number ratio, if we multiply 1.00 and 1.61 by 5, we get a 5 to 8 carbon to hydrogen ratio. C5H8 would be the empirical formula. Okay, take a look at the question, pause it, have a go, press play when you're ready. Welcome back. So it's useful to know the formula, or the equation rather, for the formation of a polymer, an addition polymer. We've got N of our monomer there on the left hand side, making N repeat units of our polymer. I've used the symbols R1, R2, R3, R4 to represent any kind of atom or group. All that happens is we open up that double bond and then we have N bonds going to another repeat unit. So in this case, if we take a look at the polymer that we're trying to achieve, R1, R2, R3 are all hydrogen atoms, whereas we can see that R4 is a CH-CH2 group. So the tricky thing with this is converting this into skeletal formulae. So we can get our structure by simply substituting those R groups in for R1 to 4, and then we have to convert it back to the skeletal formula. Okay, so we figured out what our alkene was, but don't forget that we're required to give it in skeletal formula. So there is the alkene. We're also asked for the name, so we've got 4 carbons in the longest chain, so we've got bute, it's an alkene, so we've got ene. There are 2 alkene groups, so diene, butadiene, and the double bonds are in positions 1 and 3. So buta 1, 3, diene will be the name for that particular molecule. Read it, pause it, play when you're ready. Welcome back. So we've got an alkenes question and it mentions stereoisomerism, so instantly you want to be thinking about EZ or EZ isomerism. We have restricted rotation around that carbon-carbon double bond, so what could the third polymer be? We simply swap the CH2 and the H round on either the left-hand carbon or the right-hand carbon. Give a reason why this type of stereoisomerism arises. We have a restricted rotation about the carbon-carbon double bond, and I would also suggest that you should include each carbon in the carbon-carbon double bond is attached to 2 different atoms or groups. Okay, 1 point question or 1 mark question for the last bit. Have a read, have a go, press play when you're ready. Welcome back. So golf balls don't biodegrade. A lot of plastics don't biodegrade. Biodegradable polymers usually contain a functional group that can be hydrolyzed, such as in polyamides or polyesters, which you will study in the second year. But these addition polymers do not contain groups that can be hydrolyzed. The carbon-carbon bonds cannot be hydrolyzed.